Hi, Algebra 2 Honor students. This is going to be the start of Unit 10. Unit 10 is titled Sequences and Series. So if you think back to your good old Algebra 1 days, you would have learned the initial beginnings of what sequences and maybe series are all about. But of course, my job in Algebra 2 is to extend that knowledge for you and prepare you for what you might see with sequences and series in future math courses. So let's start with what is an actual sequence. You learn sequences as early as elementary school. My daughter does sequences all the time. For us, it's going to be a list of numbers that follow a specific pattern, right? I mean, when you learn sequences as a young child, you're probably looking at shapes that follow a certain pattern, maybe within colors and things like that. But for our purposes, we're going to be looking at numbers that follow very specific patterns. And one of the most classic sequences that's pretty famous in math is something called the Fibonacci sequence. Fibonacci is a famous mathematician who was able to find patterns that exist in the world that follow this setup here. So if you look at the Fibonacci sequence, we have 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. Maybe you've seen the Fibonacci sequence before, so you might be familiar with it. But my question to you is, can you figure out the pattern? And it says this one is tricky, but I have a feeling you're going to be able to figure it out. So take maybe 15 seconds, 30 seconds, hit pause if you need to, if you really want to make sure that you understand what's going on. But if you think you have the pattern, confirm that it works for all of the terms in this sequence, because I'm going to reveal my answer right now. All right, here's the pattern. The pattern is add the two previous terms together to get the next term in the list. So if you do 0 plus 1, you get 1. If you do 1 plus 1, you get 2. 1 plus 2 is 3, and 2 plus 3 is 5, and 3 plus 5 is 8, and so on and so on and so on. So I'm sure you can figure out the next few numbers as this next question implies, right? 21 plus 34, the next term would be 55 in the list. But can you write a formula to get any value of the sequence? That might take us a little bit longer to get used to if we don't remember notations and things like that for sequences. So I'm going to leave that part blank for now. But we're going to come back to this question by the end of class to see, can we come up with a way to define a sequence such that I can maybe find other terms in the sequence using a specific formula. Let's get right into then, how do we define sequences and some notations. There are really two major notations that you'll see. One is what I would call sequence notation, which I would read this as A sub n. And A sub n with that little subscript represents the nth term in the sequence and is the position number in the sequence. So if I said A sub 3, then I would be talking about the third term in the list, okay? And n has to be a natural number, by the way. Natural numbers are 1, 2, 3, 4, all integers that are positive. So we can't have like a 3.5. There's not a 3.5 term of the sequence, which I think makes sense. And I would say it's probably a little less common to see function notation, although it does come up here and there. A of n or f of n is what you might see for function notation. And n is still the position number in the sequence. So if I said a of 2, that would be the second term in the sequence, whereas I read this up here as a sub 2, or I might just say a2 pretty commonly. So what I want you to take a look at is the two different notations and saying, hey, if the position in the sequence, the value of n is 1 or 2 or 3 or 50 or n minus 1 or n, those are all things that we'll see come up in our sequences. Then what would it look like if I used sequence notation? What would it look like if I used function notation? And this will just go pretty quickly using these different subscripts and our function notation. So here's what it looks like if we use sequence notation. Apparently I forgot to fill in the third term here. I'll do that for you right now. That would be A3. So we get A1, A2, A3, A50, A sub n minus 1. This is AN, A sub n plus 1. So we can fill those in as subscripts pretty easily. This is, again, I think probably a little bit more of a common notation, something that I'll eventually stick to in this unit. But just so that you're also familiar with it in case it comes up, here's what function notation would look like for those. I really neglected the third term here, guys. F of 3, right? F of 1, F of 2, F of 3, or A of 1. It really doesn't matter. I guess it just depends on how the sequence is defined for you in the actual question. One of the other main things we have to talk about in terms of notation and vocabulary with sequences is the difference between an explicit sequence and a recursive sequence. So here's what we're going to have for explicit. An explicit formula for a sequence is written in terms of n. We like explicit formulas typically because we can find any term in the sequence pretty easily by plugging in for n. So for example, if I want to find the 50th term of a sequence, right, I can just plug in 50 for n and I'll know exactly what that number is in the list. So explicit formulas, if we're able to come up with an explicit formula for a sequence, which is not always easy, then we're kind of golden. We can find any term that we're looking for here. Okay. And by the way, you might want to also fill this in. I realize I didn't mention this earlier, but the before term and the after term, these are things that you'll see in the other type of definition that we'll talk about, recursive. You'll see this notation and just know that a sub n minus 1 is the term that comes before this one. A sub n plus 1, of course, then would be the term that's after a sub n. And you'll see both of those notation used in certain definitions of sequences. So what is recursive then? Recursive is written in terms of the previous term. So when we define sequences recursively, you need to know the term that came before it in order to find the next term in the sequence. And if that's a little vague for you, it will make more sense once we actually see specific examples where we define sequences recursively. But explicit, and sorry if that hole punch is in the way, by the way, it says recursive. These are the two main ways in which we are able to define sequences. Okay. With all that being said, let's get into some practice here. And we'll start with explicit formulas. It says at the top, a sequence is defined by the equation a of n equals 2n minus 1. So this is more of that function notation that I mentioned a moment ago. Find the first three terms of the sequence denoted by a1, a2, and a3. So if I said to find a1, the very first number in the list, if this is the definition for your sequence, you're just going to plug in 1 for n. 2 times 1 minus 1 is 1. All right, just 2 minus 1. If I say to find the second term in the sequence, a of 2, 2 times 2 is 4, minus 1 is 3. And finally, the third number in the list, a of 3, 2 times 3 is 6, and then minus 1 is 5. So you're really building a sequence here of 1, 3, 5, and so on. And eventually, if I kept going, we'd get to a term that had a value of 53. So when I ask you in part B which term has that value, the term is the value of n. So that's really what I'm looking for. What is n when the term number right here is a 53? So we can quickly figure that out for part B by setting 2n minus 1, the sequence definition, equal to 53. So what would I plug in for n here such that the value of the sequence, that number in the list, is 53? So we can quickly solve by adding the 1 to the other side. If 2n equals 54, then n must be 27. So I don't want to have to build out all the way to the 27th number in this list to figure out, oh yeah, the 27th number is 53. But a of 27, notationally, that would be the term that has 53 at that point in the list. And then finally, explain why there will not be a term that has a value of 70. Well, I'm hoping that's pretty obvious based on our list of values, 1, 3, 5, 7, 9. Yeah, you're definitely never going to get a 70 in the list, okay? So essentially, 2n minus 1 is a sequence of odd numbers. So that is a quick and simple explanation as to why we're never going to get to number 70 in our list. And one other quick note is, we can't have a half of a term. So could I plug in a number for n such that the output here would be 70? Yes, but it would have to be something 0.5. So since we can't plug that in, since we're only looking at n being a natural number, it's impossible for us to get 70 out of that. Okay. Let's go on to the next example. And this will go pretty quickly because when you get an explicit definition for a sequence, all we're doing is plugging in numbers for n and getting the output, the list of those terms. So here's a sequence a sub n equals 2 to the n. You'll notice that this is now more of a sequency type notation, okay, as opposed to the function notation that we saw up above. So if I wanted to find the first three terms, which are a1, a2, and a3, all you're going to do is you're going to plug in 1 for n, and then 2 for n, and then 3 for n. So it's 2 to the first, 2 to the second, 2 to the third, which are 2, 4, and 8 respectively, right? Using those exponents there. This will be a pattern that we explore much further in depth in this unit, so we'll see more stuff come up like this with exponents. But the first 3 numbers in the list would be 2, 4, and 8, and it would go on from there. Let's now talk about recursive formulas then. So if you have a recursive sequence that's a little bit different, remember that every term in the sequence depends on the one that came before it. You have to know the one that came before it to get to the next term. Okay. So look at how the sequence is defined. Here's a function notation f of n. F of n minus 1 is the one that comes before f of n. So if I want to find f of 2, I have to know f of 1. If I want to find f of 7, I have to know f of 6. And what am I doing? I'm taking the term that came before it and I'm adding 5. So if I have to know the term that came before it, what we'll see with recursive definitions is you have to know what the first term is. You have to have a starting place. So notice how f of 1 equals -2 is given to you, whereas in the last examples, when it was explicit, we can find the first term by just plugging in 1 for n. Here we don't have that luxury quite yet. So generate the first 5 terms of the sequence, label each with the proper notation. The first one, f of 1, we know is already -2, so that's a good start. To find f of 2, if I plug in 2 for n here, you got to plug in 2 for n there, so it would be f of 2 minus 1 plus 5. So if you didn't believe me that this is the term that comes before it, well, subtract those. 2 minus 1 is 1. So notice how to find f of 2, I'm taking the term that comes before it and adding 5. Well, f of 1 is, from up here, -2, and then plus 5 is a 3. So let's keep going on from here. F of 3 would be f of 3 minus 1 plus 5. Plug in 3 for n here, got to plug in 3 for n there. Well, 3 minus 1 is 2. Oh, okay, so to find f of 3, I have to take the term that came before it, the second term, f of 2, and add on 5. So 3 plus 5 is 8. And now you pretty much get the pattern, right? To find f of 4, you would take f of 3 and add 5. So take that last term, add 5 to get 13. And one more time, f of 5, would be the term that comes before it plus 5. So f of 4 was 13, and then plus 5 is 18. Okay. So then it says, well, use this to determine the value of f of 10 and think about how many times you've added 5 to -2 is my hint there. So to find f of 10, if I was going to do this recursively, what would I have to know? To find f of 10, I would have to know f of 9 and then add 5. But I stopped at f of 5. So I guess I could, keep going there and eventually get to f of 9. But there has to be a more efficient way to do this, and it is thinking about this hint. How many times have I added 5 to the value -2? -2 is our starting place. And by the time I get to the 10th number in the list, I've added on 5 a total of 9 times, right? If I start in the first location, by the time I get to the 10th spot in the list, I've done 9 hops of 5 to get there. So you can really quickly get that value by doing -2 plus 9 of those 5s that were added on. So -2 plus the 45 that is we know really quickly that the 10th term is 43. So what we're kind of building towards here is moving away from this recursive sequence and thinking about this is definitely more of an explicit way of finding that value real quick. And it's something that we'll build upon over the next few lessons and thinking about some patterns here. Okay, so if we turn to the next page, for example 4, given the sequence, answer the questions. I think you can probably do example 4 and example 5. So these are 2 questions that next time I see you in class, we will go over the answers, but I do want you to take about a minute or 2 minutes, however long it takes you, to answer these 2 questions right now. So hit pause, try those, but next time we're in class, I'm going to show you the answers to these 2 questions. Okay, figure out the pattern, determine the next 3 terms, and then think about how would I get the 100th term? Use the logic that I used in this example right here. See if you can help yourself out there. And then try this one. Just notice how this is a recursive sequence. How do I know it's a recursive sequence? We're told what the first term is. Notice how the recursive sequence is a little bit different as compared to the other one we did. A sub n is the one that comes before this term right here, a sub n plus 1. So that might take a little while to get used to, but see if you can give it a shot. If you're confused, we'll go over it next time we're together. Let's go through example 6, though. It says, given the explicit formula, answer the questions, determine the first 5 terms of the sequence. This should go pretty fast for us. So just plugging in 1, 2, 3, 4, and 5 for n to get the terms here. So what would a of 1 be? It would be 5 times 1 plus 1, which is 6. And then a of 2 would be 5 times 2 plus 1, so that's going to be 11. And what we'll notice really quickly is all that's happening when I find these terms is that you're adding on 5 each time. So if we have that starting place, 15 plus 1 is 16, and you can quickly generate that a of 4, therefore, is 21, and that a of 5 is 26. So we can get that list pretty quickly. If you don't believe me, of course, plug in 1 through 5. But I like this last question. It says, write a recursive formula to represent the sequence. And that takes a little while to get used to. How do we write recursive formulas? Well, when I write a recursive formula, you have to know what the first term is. So the first term is, in this example, 6. But what am I doing to each from the first term to get to all the next terms? What I said as far as a pattern goes is that we're consistently adding 5, adding 5, adding 5. So if I start with the term a sub n, I'm going to use the sequence notation. I'll also use function notation for you guys if you like that. So a sub n, I have to take the term that came before it, which notationally is a sub n minus 1, and then add 5. And we should be able to confirm that if I go and check this, that I get this list as long as we define that A1 equals 6. If you don't define A1, we have no place to go. We can't generate terms in a recursive formula without being told A1. So that's a pretty important thing to pay attention to, that, okay, if A1 equals 6, then I have enough information to be able to generate the terms in this list. Or if you like the function notation, you would have said that a of n, like this, equals a of n minus 1 plus 5. Still have to define that a of 1 equals 6. Either of those two notations, unless it says specifically to use function or the sequence notation, you can choose whatever one you like. All right. Last thing we're going to do today is we're going to go back to something we talked about in the beginning is, hey, what about that Fibonacci sequence? Write a recursive formula to represent the pattern. And you know what? I'll let you think about this one too. I'll keep you in suspense. Think about the Fibonacci sequence. Can you define it recursively? You're going to need a couple extra things there because remember, it depends on adding 2 terms together to get to the next term. So think about a recursive definition there. I'm going to ask you for some help next time I see you in class. Hopefully this is bringing back some good memories for you as our initial start to sequences. A lot more to come in this unit. Have a great rest of your day.